Right then, we're looking at the moment generating function of a discrete uniform distribution. So this random variable x follows a discrete uniform, taking the values 1, 2, 3 up to n, and the probability of each outcome is the same, so it's that 1 over n. An example of where you've seen this in class is probably where x is the outcome of a die, and you've got values 1 to 6, and each of the probabilities is the same at 1 over 6. We're going to show that for the discrete uniform, the MGF is given by this expression, where t for t not 0, where t is 0, the MGF takes the value 0. In doing this proof, we'll pick up on some interesting results from math. Right then, MGF, write down definition. MGF is equal to the expected value of e times t to the times the random variable, which is called x here. Now, x is discrete, the random variable is discrete, so we're going to use sum and not integral. Then we'll write down this thing and write down, multiply it by the probability mass function. And it's summed over x. Well, we know that the possible values of x here is 1, 2, 3, all the way up to n. Okay. Now substitute for this guy, but we already know that's 1 over n. I could put 1 over n here, but I realise that this sum is for x. And since 1 over n does not depend on x, it's a constant. So it's like a common factor in each of these, each term. So we can bring it out. In other words, just another way to express that is just use the summation rule. Okay, so the constant does not depend on x, so take it out. E to the tx. Okay, so we've got a sum here. We want to kind of rewrite this thing so it does not involve x, because the MGF is only a function of t, not of x. Let's see. So it's a sum. We know it's a finite sum as opposed to infinite sums. So you see in statistics we have kind of like two kinds of sums. We're interested in finite and infinite. Okay, so we need a kind of a formula for this thing. So this is something that you might know from college or school, a result of the sum. I never memorize it, I kind of always try to derive it. So let's call this whole thing, I'll put it on the side since it's not the main part of the proof. Say e to the t to the power of x. Okay, and that looks messy, so let me just say that this e to the t, let's just call it, it's just a number, let's call it a, because I want to write it so you can see it's of this form. And now we want a formula for this sum here. So sum of x equals 1 a to the x. This starts looking like, if I start writing out with a summation sign, a plus a squared plus n, an, the final term. Which you can see here is a common factor of a, that can be brought out. 1 plus a plus a n minus 1. Now some of you hopefully recognize this as, you know, you're thinking about infinite sum, geometric progression, that kind of stuff. Only this here is not a infinite, it's a finite. But the proof for the formula of this thing is going to be the same as you've seen for the infinite case. Let's just draw the line like this. Right, let's call this S for sum, this guy here. We want basically a formula for S. A nice neat formula. Okay. Well, let's consider AS. You can see that AS, that's going to be a squared. 1 plus a plus n minus 1. Now the idea is that if we look at S minus AS, you'll see that the terms, all the terms apart from 2 will cancel. The term we're left with is a minus a n plus 1. Okay, this guy here, common factor of S, so that can be brought out. And we have this. Of course you could tidy this up as well, but I don't need to. So therefore, we'll finally get an expression of s in terms of a like this. If I want to tidy up the numerator, that's common factor of a again, so 1 minus a to the n 1 minus a. And notice, unlike for the infinite geometric progression, we don't have any restrictions on a. We're not saying that absolute value of a has to be less than 1. We're not saying that. It can be bigger than 1. This proof here works. Let's see, it works so long as a is not 1, right? Because if 1, it'll be 1 minus 1, which is 0. Because we're dividing here this thing through by 1 minus a, so we don't want a for a not equal to 1. Okay. If we go over here now and use that result, so the a here is e to the t, you can see that what we have is 1 over n. In fact, we'll just have the result, we'll just write it down. So replace a here by e to the t, and we're done. N t 1 minus e to the t. Here it's e to the nt because recall the rule e, let's see, to the t to the n. That's the same as just multiplying it like that. And the general rule is I don't even need to have the special e. E is just a number, remember. So if we have any general number, what should we call it? And a general number, usually it's called a, isn't it? A to the t to the n will be a times t to the n. Okay, you can just check that on your calculator if you're not sure. So if t is 3, n is 4, that's the same as, do that on your calculator, 2 cubed and then power of 4 on that is the same as 2 to the power of 12. Okay, and now what we notice here is that this is going to be fine so long as t is not 0. Why? Because if t is 0, it'll be e to the 0, which is 1. 1 minus 1 is 0. And then up there you're going to have 1 minus 1 as well. So in other words, for t is equal to 0, you got a problem. At t equal to 0, we have, if we just look at it, equals to 0 over 0.